So carbon's an increasingly discussed topic within agriculture. Carbon has a unique ability to bond not only to itself but to almost any other element, and as a consequence it's a part of every compound that's essential for life. The carbohydrates, proteins, even the nucleic acids that make up the DNA that passes on our genetic blueprint from generation to generation. And carbon also forms the building blocks of your soil life and indeed your soil health. So today, let's take a look at some of those building blocks, talk about how we might perform analysis of those blocks and how that information could be useful to you and your soil health regeneration projects. So we think about the carbon stock within our soils. That could range from a few tons per hectare of topsoil up to many hundreds of tons into a very rich, fertile environment. But carbon exists in the soil in many different forms. So let's try and break down those different forms, find out which ones are more useful to us, which ones we can manage, which ones we have to manage with, and discuss how we can use the analytical information that we produce at Landcrop Laboratories to help you make management decisions. So the first building block we should look at is our inorganic carbon content of our soils. So this is carbon that's present in the form of shales, canal coals, lignites, but also carbon that makes up the carbonate inclusions in chalky, brash, calcareous soils. Now, we can't manage this carbon. This carbon is determined by the geology of the land that we're farming upon. This carbon has been put down over millennia of geological processes, but we certainly have to manage with it. And in particular, if we're on chalky soils where there are high amounts of inorganic carbonates, then the associated cations that go with that carbonate, things such as calcium or magnesium, can impact upon our nutrient management decisions. Soluble calcium can react with soluble plant available phosphates, locking them up. They can reduce the availability of key micronutrients such as copper, manganese and zinc. So if we have a high presence of this inorganic carbon, we should consider this as part of our nutrient management, and we might want to think about our phosphate approach using maybe protected phosphorus products or maybe seed treatments or even foliar applications within our nutrient programs. So if we've got inorganic carbon, we also have organic carbon. This is the carbon that makes up the organic matter within the soil. And indeed, it's this that makes soil what it is, soil. Without the organic matter, what do we have? We simply have ground up rock, in essence desert. And if we lose key stocks of organic matter from our soils lose their fertility, they lose their aggregation, they become less robust and more prone to erosion. And we can lose valuable topsoil to wind and water erosion. So organic matter makes soil what it is. But organic matter is also the habitat and the food source for the essential soil life, the soil biology within our soils that drives the processes that make soils a thriving, living ecosystem in their own right. And together they bring us many benefits. They help with water regulation, holding onto water, soaking it up like a sponge, so we have access to it in times of drought. And when we have excessive water events, they help move water away and percolate through the profile. So the organic matter reduces the bulk density of our soils, making them easier to work, easier to traffic, and also increases their resistance to compaction. Organic matter can render inert some of the active compounds that we apply to soils, ensuring that they don't enter the local water system. Organic matter also acts as a nutrient reserve, holding onto it significant quantities of vital nitrogen, phosphorus, sulfur and other key nutrients, but all there in an unavailable organic form, waiting to be released into a plant available form. And for that to happen, we need an active aerobic soil biology. And we can measure that in the lab by measuring the respiration rate of your soils. So here's our next soil carbon building block, respired carbon. A good biology is just like me, it's just like you. It breathes in oxygen and it breathes out carbon dioxide. So although we increasingly are looking to manage the losses of carbon into the atmosphere, this is an essential loss. A healthy soil will respire and lose carbon in the form of carbon dioxide. And we can now measure that rate in the laboratory. We take your soil, your standard soil sample, which you have to take now to satisfy water directive rules and increasingly now as part of the ELMS protocols. And we can measure the rate at which carbon dioxide is released from this soil under very controlled conditions. If we know the rate at which carbon dioxide has been released from your soils, that is an indicator of the aerobic microbial biomass within your soils. Quite simply, we can tell you, do you have high levels of life or do you have low levels of life? And it's this life I like to think as being the canary in the mine. We can't see these microbes, but if we can measure their activity, measure their levels, we can use this as an indicator as to whether conditions are improving or whether our soil conditions are deteriorating. Because these microbial populations are sensitive to levels of acidity, they're sensitive to compaction, they're sensitive to poor drainage, to waterlogging, and they also require fresh carbon inputs. So if we see these microbial populations declining, that's an indicator to us that we need to make some decisions and start to improve our soil health journey. If we have a microbial population, we need to feed it. And there's our next carbon building block. And this is the active carbon within your soils. So this is the simplest carbon compounds that are there once we have complete carbon cycling in a form ready to feed that microbial biomass. But this is most commonly supplemented by root exudates, where we have a healthy canopy, green cover within the field, photosynthesizing, trapping carbon dioxide from the atmosphere, converting it into energy through the form of photosynthesis, and then this excess carbon in the form of sugars is released via the roots into the soil, into the rhizosphere to support that biology. Why does the plant do that? Well, it wants to support a healthy biology because in return, that biology will deliver nutrients, water, to those growing roots, and it will build a healthier, more structured soil within those roots to explore. So it's a symbiotic relationship between the microbiology and the plant itself. Plant delivers sugar, the microbiology delivers benefits. So there we have it. The 5 building blocks of your soil carbon, from slow turnover to rapid, fast turnover, those that we can manage and those we have to manage with. So hopefully by using these analytical tools on your standard soil test reports, they can help you make positive decisions on your soil health journey.